So, today we are going to discuss on intermediate phases, and many of these intermediate phases forms in the peritectic phase diagrams. This is the reason we need to discuss about these phases here itself. There are few intermediate phases which forms by the monotectic and syntectic reactions, but they are very less and not very useful. All the useful and industrially important materials or intermediate phases normally comes from the peritectic reactions, and that is the reason actually I want to discuss it here. But let me just first draw the two peritectic phase diagrams, the one which I have already shown you and the new one also. So, first let me draw that one which I have shown you for the last one lecture. So, this is the classical peritectic phase diagram with a peritectic reaction. So, this is the liquid. Let me first draw the melting temperatures of A and B, liquid, alpha, beta, and this is alpha plus liquid, this is beta, liquid plus beta, correct. So, this has a peritectic reaction at the peri temperature Tp. But I told you that most of the peritectic reactions are followed by a eutectic reaction. So, and this is where the intermediate phases forms. So, let me again draw the modification of this diagram or little different from this. So, first is again remains same, then you have this, and there is a separate okay. So, this is what I am trying to say. So, the melting temperature of A, melting temperature of B, liquid, alpha, this is the beta, therefore, this is liquid plus alpha, alpha plus beta, and there is a new phase gamma, correct. So, this phase forms by eutectic reaction from the liquid, okay. So, therefore, this will be beta plus liquid, this is liquid plus gamma. Now, I am talking about this phase which is formed here, beta, which is distinctly different from this. You can see here beta is composition is only sitting at the center of the compositional axis xb almost, and it has a small span. It is not exactly a line, it has a small span of composition in which it is stable, and this normally has a different crystal structure. So, such a kind of phases are called intermediate phase. The reason it is called intermediate phase is because of this. We know that there are two solutions at the end or at the terminal positions of A and B respectively. One is alpha, which is a resolution solution, other one is gamma, which is a p resolution solution. Now, this phase comes in between of this composition or intermediate compositions of these two solutions. The beta comes intermediate compositions of alpha and gamma, and that is why it is called intermediate phase. And because it is does not have a fixed stoichiometric composition like sodium chloride, potassium chloride or any other phases, it is called intermediate phase. Okay. So, intermediate phase means its compositions lies intermediate of two solutions at the ends. So, first is the composition lies in the intermediate region of two terminal solutions. That is the first thing you will see for this kind of phases, and this is very common, which I will show you very quick after some time how these phases will appear in the phase diagram. So, this is the first condition to be satisfied for an intermediate phase. Second condition to be satisfied is that this phase is stable for a small compositional range. What I mean to say is, this is not a compound exactly. If it is a compound, then it will have a fixed composition, but it is not. It has a range of composition in which it is stable. It may be 2%, it may be 1%, it may be 3%, does not matter, but it has. Third important criterion to be satisfied by these kind of phases is that the crystal structure of this phase is distinctly different from the terminal solution. And therefore, they are distinctly different phases. They are not same as either of these two terminal solutions, they are distinctly different phases. So, you have already got an idea that such a kind of phases exist in the peritectic phase diagram. As you see here, it forms by peritectic reaction. In fact, this phase diagram I have already shown you at the beginning, that is for the iron germanium phase diagram, in which there is a phase called epsilon which forms out of the peritectic reaction between alpha and liquid. So, in this case beta is a solution which has extend from this to this, but in this case beta is an intermediate phase, it is not a solution. That is the difference you must make out from this diagram. Here beta forms by this reaction, here also beta forms by this reaction, same reaction, but the things are different. One example of this is in hafnium tungsten phase diagram. There is a phase called HFW2 forms as a reaction, peritectic reaction. So, there are many host of phases. Now, with this brief introduction I have given you, let me just show you few phase diagram where such a kind of phases exist, and then we will discuss further. Okay, so let me just take you through the phase diagrams, so which will come alone, and here it is. This is the first phase diagram I am showing you, aluminum nickel. You can see here I have written many phases like Al3Ni, Al3Ni2, Al3Ni5 and Ni3Al. All of these phases formed by peritectic reaction, all, okay. But you see Al3Ni is a line, as a line like this is a line compound, Al3Ni5 also is a line compound. Okay, but on the other hand Al3Ni2 and Ni3Al has a stoichiometric, has a compositional range in which it is stable. It is not only a line, but there is a domain range of composition is stable. Okay, so therefore these phases are called intermediate phases because their composition lies in between the solutions of nickel and aluminum. There is another phase called Al-Ni here with composition Al-Ni who has a large compositional stability range. It is not forming by peritectic reaction by a different one, is called congruent solidification or congruent melted compounds. It directly forms from the liquid, but all of them forms by peritectic reaction. Here you see there is a peritectic reaction, there is a peritectic reaction, there is a peritectic reaction, and there is a peritectic reaction there. So, this is a classic phase diagram, but you know all of these are useful material. Most important one is Ni3Al, which is used in the real applications. All the turbine blades which is used in the steam generators or even the jet engines, they are made of this alloy Ni3Al precipitates. Gamma graphamine precipitates, you might have heard about it. So, gamma is this FCC solution of nickel, okay, and gamma prime is this Ni3Al precipitate. So, this is the first example. Remember these phase diagrams all are available online from the SGT website or FactStage website. So, you do not need to look into any book, they are available free. Now, let us move on. There is another compound here I am showing you for Mg tin system phase diagrams. You see here there are two eutectic reactions in Mg tin system. Eutectic I have already discussed, and in between there is a compound Mg2Sn as a line, okay, is a fixed stoichiometric compositions. So therefore there are many intermediate phases where these fixed stoichiometric compositions are maintained, but as I told you at the very beginning, that is not necessarily the condition to be satisfied by the intermediate phases. There can have compositional domain range, but examples do exist where the compositions is fixed and then there is a line in the phase diagram. So whenever you see a line, that means there is a fixed stoichiometric compositions for the phase existing. So here Mg2Sn is forms at the fixed compositions. It has a eutectic reaction between the solutions of pure Mg, pure Mg is alpha Mg, okay, plus Mg2Sn. On the other hand, here you can see it is Mg2Sn plus the tin phase. So Mg2Sn plus beta tin is the eutectic. Very simple phase diagrams, only difference is that there is an intermediate phase at the center, almost 33% of tin. Now for aluminum copper there are many phases, I cannot discuss even that. So region I marked like a magenta color circle, there are many, let us not discuss. The starting one is Al2Cu, and it has higher temperature, it has a slightly larger compositional stability zone, but lower temperature it has a fixed compositions. Then you have Al9Cu11, Al2Cu3, there are many others phases which exist with a compositional range, and some of them AlCu see or AlCu forms by Peritectic reaction, even Al9Cu11 it forms not by some other reactions, but on the other hand Al2Cu3 is formed by Peritectic reaction. So most of the intermediate phases forms by Peritectic reactions. Now another important phase diagram where these intermediate compounds exist in large or in several ones exist in aluminum iron. This is what I am showing you. You can see there is Al3Fe, Al5Fe2, AlFe2 present, and there is another one Al5Fe4 at the top, correct. So all of these are actually intermediate phase, and this one, also this one, all of these of three are, or even this one, all of them actually here are forming by Peritectic reactions. So you have to simply look into their phase diagram database or data to see what is the which phase it reacts with the liquid and form these Peritectic reactions. Sometime Al3Fe is written as Al13Fe4 because of compositional deviations, but you can see Al3Fe has a compositional range. On the other hand, the other two has no compositional range in which it is stable, but it is stable only for a fixed composition. That is Al3Fe. Now let us look at, this is another very classic phase diagrams, MgNi. MgNi has two intermediate phase, Mg2Sn for a tin composition of 33% and Mg3Sn tin concentrations of about 66.66% of tin here, and these are called Laves phases, which we will discuss later, what is Laves and who discovered and how, what are the characteristics of that. But you know both of these two phases has eutectic on the two ends, correct, but these also forms by Peritectic reaction, this also forms by Peritectic reaction. Now this does not form, this forms congruently from directly from the liquid, but this forms by Peritectic reaction Mg2Sn. Mgzn again a complex phase diagram, but one can see there are several phases, Mg12Zn3, Mg2Zn3, Mg2Zn11, this definitely formed by Peritectic reaction, this definitely formed by Peritectic reaction, this one also, all of them. And there is another phase at the center which does not form a Peritectic reaction, but by congruent melting, congruent solidification is Laves C14 phase, which has a composition about 66% zinc and rest of tin. So it will be Mg3 what Mg3Zn, this composition it will have Laves phase. So you can clearly, and then there are others like silver magnesium, most of them are actually with magnesium, Ag3Mg, AgMg3, there are two, and AgMg at the center, but these two Ag3Mg and AgMg3 they are almost like a line, but AgMg has a large compositional domain. But AgMg does not form by Petri reaction, it formed by some other thing like incremental solidification, which we will discuss later. Silver copper I have shown you. Okay. Now, so therefore, all these phase diagrams I showed you, I will again showing you one more time, just to flashing you to make you believe that these are actually real phase diagram, and these phases exist in the real phase diagram database. So thus it is important for us to understand them. So now with giving these examples of intermediate phases, let me just tell you that we can classify them, because you are flooded with many phases and compositions. So we can classify them as 3 types, and that is what I am going to write you on the board, and this is very important lesson, you should remember, you should not forget. Okay, this is very important because these are the data not available in many books, which I am going to give it from this particular sheet, which I have taken down from the textbook. So there are 3 types of intermediate phases classically. The first one is known as valency type. First one is known as valency type, or valency compound they are called, because they follow typical valency rule. What is that? If you consider sodium and chloride, sodium loses 1 electron and becomes octet at the outer shell, and chlorine takes that 1 electron, become octet in the outer shell. That is how sodium become plus ion, positive ion, and chlorine becomes negative charged ion, and then there is a natural attraction and it forms a compound. So that is actually called a valence compound, because valency is or electron transfer takes place at the valence band. So there are many such compounds which obey this rule, okay, and they can be of these 2 compositions, NaCl or CF2, sodium chloride or calcium fluoride compositions. Both are ionic compounds, both are actually valency compounds. I will give you examples in intermetallic phases. These are Mg2Si, magnesium 2, Mg2Sn I have shown you. So Mg2Sn is a valence compound which exists in magnesium zinc diagram, and Mg2Pb another one, and last one is Mg3 3Sb2 magnesium antimonides. These are very important, antimonides are actually thermoelectric materials, they are useful. So the first type of compounds, they are called valency. Second one is known as size factor compound. Why they are called size factor compounds? Because they are stabilized by size factors, or difference of sizes of the atoms, different sizes of atoms. Just like we know that different ions are stabilized by the size factor, so similarly these are also stabilized by size factor. Okay, and these are actually called Laves phases, because scientists called Laves first time discovered these phases, that is why it is called Laves phases. So they are stabilized by size difference, relative sizes of the atoms. Correct, there are 2 types of Laves phases, and all of them will have a composition AB2 type, all of them. That is another classic, another important aspect of Laves phase. All of them will have composition AB2 type, where A is the large atom and B is the small atom. Okay, very simple to remember, AB2. Now what are these are? Okay, these are very simple. There are many examples. First let me get an example, then I will talk about the structures. MgCu2 type, they are cubic, and then MgZn2 type, these are hexagonal, and last one is MgNi2 type. This is also hexagonal but double unit cell, which we will show you later, or maybe today itself is possible, this is lecture. So this is cubic, all of them has composition AB2, MgCu2, MgZn2, MgNi2. all of them. So all of them all the cubic phases which are of this type size factor can be classified under MgCu2. They are titanium, beryllium 2, silver, beryllium 2 and bismuth, gold 2, all cubic and all of them have similar structure. Here this is gallium, magnesium 2, tantalum, Fe2 and niobium, manganese 2. Some of them are superconductors by the way, and some of them are very interesting materials. The last category is Nb, Zn2, selenium, iron 2 and hafnium, gallium 2, Cr2. Okay. So there are, so you can clearly see that actually that these are the 3 different types of size factor compounds, okay, which are stabilized by the relative size of the atom. MgCu2 type which are cubic, other 2 Mgzn2 and Mgni2 are hexagonal type, and these are the examples. So last one is called valency, or this called electron compounds, because they are stabilized by electron to atom ratio. Electron compounds, or it is known as Hume-Rothery compounds. Hume-Rothery was the person who discovered it, Hume-Rothery compounds, and they are stabilized by E by A ratio. What is E by ratio? E is the valence electron, number of valence electron, and A is the number of atoms in the molecule. That is what is the factor which stabilizes. It is not easy to explain this. This basically depends on Brillouin zone and the interaction between Brillouin zone and the outer electron surface, the many things, but I am not going to details of that, but this is mostly stabilized by E by ratio, and there are 3 E by ratio only at which this compound is stabilized. These 3 E by ratios are 3:2, so there are 3 E by ratio, 3:2, 21:13, 21:13, and last one is 3:2, 21:13, last one is something else we will see, and what is that? I think 2/3, yeah, correct. So there are 3 ratios, sorry, not 2/3, it's 7:4, yeah, sometimes I also forget, 7:4, so there are 3 which these compounds are stable. So let us see some of the examples which will be clear to you, correct. So first example of this actually is, I will give you copper zinc. How it is 3/2? Okay. There are 2 atoms, copper has 1 electron in the outer cell, zinc has 2 electrons in the outer cell, so 2 plus 3 is 3, and there are 2 atoms, so it has become 3/2. Okay. So and then this is another phase of copper zinc, let me tell you, Cu9 Zn8, Zn, what is the number? Cu9 Al4. How it is? So 9 plus 4 is 13 atoms in the unit, A is 13 and 21 is how much? 9, so U has 1 electron, outer cell electron, so 9 into 1 and 4 into 3, 12. So 12 plus 9 is 21 divided by 9 plus 4 is 13. So it's 21:13. That is what is stabilizing it. And let us see the 7/2. Okay, 7/2 is Cu3Si. How it is 7/4? 4 is obviously 3 plus 1 is 4, 3 atoms of copper, 1 atoms of silicon, and the 7 is 3 plus silicon has 4 electrons outer cell, 7 plus 3 plus 4 is 7. So 7 electrons in the outer cell divided by 4 atoms, correct. So, this is what is the 3 ratios in which these compounds are stable, and in the next class I am going to show you the structure as well as I am going to show you some more example how to calculate and look into it.